Describe the composition of ideal alveolar and mixed expired gases. So the definition of this is the uniform composition of a gas that would exist in all alveoli for a given total respiratory exchange if all alveoli had identical ventilation perfusion ratios and achieved perfect equilibrium with the blood leaving the pulmonary capillaries. So that's obviously a bit of a mouthful of a definition. I don't think I've ever been asked that, or yeah, it's a very nice theoretical concept. So I think we'll just move on from that anyway. So
and can I just clarify, that's them having identical VQ ratios, not having a VQ ratio equal to 1?
Yeah, that's right. So they're just saying have your respiratory exchange, whatever it is, but it's a uniform gas, so all the VQ ratios are perfect or identical.
Yeah.
Yeah.
I did want to ask that because in nuns it looks like it's inferring the VQ is 0.8, and that would make sense with that. But in other areas that you read, it says that the VQ would be 1. So I did want to ask what your opinion was. So 0.8, if we're asked specifically, we should say for a VQ ratio.
And again, because I'm not a respiratory physiologist, it's hard for me to say what the answer is except my personal opinion of it. And I think I'd agree with the statement that normal lungs have an average of respiratory exchange of 0.8, a VQ of 0.8, sorry. Therefore, that is what normality is. Though you could argue that 1 is perfectly normal or better kind of normal, but I think I'd just go with 0.8. But yeah, I don't have a good answer to that. So yeah, does everyone want to have a go at just writing out the alveolar gas equation? Because that'll be important. So yeah, just take a few seconds to do that. So essentially, I'll ask you what the alveolar gas equation is. I'll ask you what is F. That's a factor at the end. If you do know it, that'll be interesting. What is a typical PaCO2? And then talk about each of the components, the saturated vapor pressure at altitude at 35 degrees.
So I've just written the equation, which is PaO2 equals FiO2 times the pressure, atmospheric or barometric pressure, minus the saturated vapor pressure of water, minus partial pressure of CO2 in the arterial blood over the respiratory quotient, plus the correction factor F, which is PaCO2 times FiO2 plus 1 minus the respiratory quotient over the respiratory quotient.
Mm-hmm. That's good.
And then and then you could just plug in the normal value.
Great, so PaO2, and I just feel like this is one of those equations that, like the Hagen-Purcell equation or the fixed law of diffusion, just comes up time and time again. So yeah, you're right. It's barometric pressure times the fraction of oxygen multiplied barometric pressure minus the saturated vapor pressure. Take away PaCO2 over R plus this correction factor, and F. What is that usually equal to?
F.
Yeah.
Yeah, so normally approximately 2 millimeters of mercury, but as I said, if you increase your PaCO2 or you increase your FiO2, it goes up.
Yep. And so roughly, if you're having 100% Fi, what is it approximately?
I think you can get up to 10.
That's exactly right. Yeah. So normal 2, you can get up to 10 with a really high Fi, and obviously with that equation, it will also rise with large PaCO2. Good. And what's a typical PaCO2?
Approximately, PaCO2, approximately 40. So yeah.
Exactly. Yeah. And so what does that number then, PaCO2 over R, usually become?
PaCO2 over R.
Yeah, that's right. Like divided by 0.8.
Oh, sorry. Yeah, 50.
Yeah, exactly. It's nice to know roughly what each of these values becomes. Which it can get you through this kind of exam part quickly. What does saturated vapor pressure depend on?
So it depends on the barometric pressure and the temperature.
That's good.
And the way I remember it is, I think it's Armstrong's limit, which was that pilot who discovered, I think it's like 19,200 meters. He blacked out when he was flying one of the first high level missions, because the last thing he remembers was his saliva evaporating in front of his face.
Oh, wow.
So if you decrease the barometric pressure, then your boiling point also decreases.
Yes.
So at that level, body fluid boils at room temperature, essentially. Oh, sorry, body temperature, 37 degrees.
What was that? What was that altitude that
It was 19,200 meters approximately, I think. Yeah, 19 Ks.
Did he survive?
Yeah. He blacked out, and then the plane went down, and then he regained consciousness once the pressure increased.
Oh, that's nice. That's reassuring. What value? So the normal value is 47. How about 35 degrees? What's the value?
So I don't know, but I imagine that it would increase.
Are you sure?
No. Not the way you asked me the question. It would decrease.
So it decreases to 42 millimeters mercury.
Yeah.
Can I just clarify for at altitude, is it that the saturated vapor pressure actually increases, or it just becomes a larger fraction of a smaller total atmospheric pressure? So is it that at 19 Ks up in the air, the atmospheric pressure is just equal to 47, and so the entire volume of gas within your lung is just water and nothing else?
Yeah, that's a good question. So if
you're right.
Things will boil when your saturated vapor pressure equals
atmospheric pressure.
Yeah, that's right. So
like, would you actually say that the saturated vapor pressure doesn't change according to altitude? It just becomes the fraction of your mix changes?
You're right. So at altitude, your saturated vapor pressure is exactly the same. It will just have implications like we mentioned. So yeah.
So when we describe just like phrasing this in a viva, when you say, the saturated vapor pressure of water, I think Rudy said at sea level is this. Would it be better to say at body temperature, because realistically altitude won't affect your saturated vapor pressure?
That is correct. So when I wrote this question, it was the fact that at altitude it remains the same, but with temperature it will change. So that's exactly right.
Cool. Thanks a lot.
Okay, good. Okay, so moving on. Actually, so this is something I actually didn't really, when I looked at PaCO2 over R, I didn't really think about what this meant in any, in any detail. Like, for example, this would assume that if my CO2 climbs, if my CO2 rises, then my PaO2 will decrease, will decrease. Now, recently I had a chat with Stan Tay, and we're kind of discussing this, and so one of the things that realistically occurs is the fact that when you say you have someone on one lung ventilator. This is a particular example because I remember this is what we had to do is a thoracic case, double Lyman tubes in the lung, and they just need lungs off for a ridiculous amount of time. So I had the patient not ventilating for about 20 minutes or so. And in that time, the CO2 climbed, and I think someone mentioned the value, but just to reiterate, how much does CO2 climb every minute approximately of apnea?
Yeah, so I think I said 3 to 4 millimeters mercury.
Okay, great. And so literally the CO2 started at, let's say 40, and at 20 minutes, almost exactly 20 minutes, the surgeon said, yep, lungs on. And at that point, we took a blood gas, and the CO2 had literally risen 20 minutes times 4. So 20 times 4, 80 plus 40, 120. So it was 120 was my, P arterial CO2. Now, at the whole time, the saturations were 100%. Like there was just no problems with my oxygenation. I can't remember, I should have taken I took a guess. I just can't remember what the actual PaO2 was, but it wasn't substantially lower. So what do people make of that?
I've heard Stan Tay's thoughts on this topic. I think during a pregnancy physiology Zoom session last year. I think the way that he described it, which I don't think I understood until about 2 weeks ago, was the thought that, realistically in this equation, PaCO2 is being used as a reflection under normal circumstances of the exchange between oxygen and CO2, as opposed to directly reflecting the composition of partial pressures at the alveolar level.
That's a really good way of explaining it. Okay, so that's
and
really good.
I tried to work around the difference of what would happen if you just hyperventilated somebody severely versus if you just injected a whole bunch of CO2 into their blood, and the amount of displacement of oxygen by just adding a bunch of extra CO2. The effects are much less significant, kind of like the same way we account for water displacing oxygen. It results in a really tiny change in your alveolar oxygen.
Yeah, good. And so this is definitely not something to get into in the exam. Maybe examiners don't even care about this particularly. Again, we're not respiratory physiologists. We're just taking these textbooks and applying them to these questions to give you guys a nice little hurdle. So, obviously don't need to get into this a lot, but I think that's a good explanation. It's a reflection of the CO2 and oxygen exchange over normal circumstances rather than any acute rises in anything in particular. And take that example, I've got a patient who's apneic, CO2 is rising, but essentially I'm giving oxygen access to the alveolar membrane through high flow and through enough flows and 100% oxygen, and the saturations just aren't decreasing because there's still the appropriate metabolism and appropriate exchange. So even though I'm not ventilating, my oxygen is still getting to the alveolar barrier for exchange.
I must admit, I haven't fully reconciled what Stan has to say about this with my own understanding of respiratory physiology. In that I agree with you, your patient maintained their saturations, but mainly probably because you had them on a FiO2 of, probably 100%, during that time. And therefore a large reservoir of oxygen, before they were able to, desaturate. Meanwhile, I agree that, the difference between alveolar and arterial CO2 can be different. Is pretty soluble. So you'd expect that, any increase in the blood CO2 would be quickly reflected in the alveolar CO2, right?
Yeah, there's not much gradient.
Yeah, exactly. And then, but increases in CO2 deposition in the lung are just going to increase the volume of the lung, which is going to cause passive expiration if the volume actually increases in the chest. As per if you're not ventilating a patient and they'll just return back to FRC, what's more likely is that oxygen comes in, less CO2 comes out, as per the RQ, and therefore you get passive oxygenation of oxygen coming in by the airways, apneic oxygenation. So I haven't quite understood why he thinks this is not applicable in, real life physiology yet.
And so I've got to say, I haven't fully reconciled it either. I think I'm going to have more chats and, have more of a think about it, and maybe even do a bit of an experiment at work situation if I have to get someone apneic. So yeah, you're right. Mine's a very specific circumstance. I haven't really gathered all the data for that. So let's all go away, think about it.
I'm glad that it's not just me who's confused then.
And the problem is, again, we're trying to model things that are actually really complicated and fluid, and
absolutely,
it's it can be very unsatisfying at times. Yeah, let's go to this. So describe the oxygen cascade. Great. So again, definitions I've got here: the stepwise decrease of the PO2 from atmosphere to the mitochondria. So just a nice brief definition that helps me to explain it. So I want you guys to draw the graph. Actually, I'll get you to draw the graph and ask you a whole bunch of questions from that. So yeah, just take 2 minutes here.
Basically I've drawn a little diagram like this.
Excellent.
Where you have the atmospheric pressure coming in here and the factors that, and that's the millimeters of mercury of oxygen. And so say if we go with atmospheric pressure and just room air, then you'd be starting around 150. This first one is the vapor pressure of water as you humidify down into the airway, so that's 47. So you take that away, and then you have the component of CO2 from the alveolar gas equation, so you take about 50 off there. Next, you need to account for any venous admixture and shunt. And depending on kind of whether the lung is healthy or not, you'd have potentially in the healthy patient about 5 millimeters mercury of difference.
Yep.
And so you get to you would get to left atrial kind of arterial O2. And then what do I have next? So then that's a value of 80, for example, in the healthy person or something in that range. And then you would get to the capillary level where gas exchange occurs. You have diffusion across into the mitochondrion for that could be anywhere between kind of 1 to 30, I think. And then you go back to venous blood, which has a PO2 of 40.
So it would be bad if it was 1, because that would be, why would it be bad if it was 1 millimeter mercury?
Sorry?
Why would it be why would it be bad if the partial pressure of oxygen at the mitochondria was 1?
Why would it be bad? Well, you'd be running out of kind of ability to do aerobic respiration.
Yeah, that's right. What point is that called?
I think it's the critical point, is it?
It's called Pasteur's point.
Okay.
And it is a critical point, you're right, but Pasteur's point, so the PO2 below which oxidative phosphorylation occurs. Now just with, I couldn't see on your graph because I've just got it quite small on the screen here. So on your x-axis, obviously locations. So, air to, humidified inside the lung. At the point of P, there's a drop from P, the pressure of oxygen from the alveolus to the pulmonary capillary arterial pressure. Why is there a drop from there to there?
So that would be the diffusion barrier.
Yeah, absolutely. Excellent. And how about from P alveolus, so PaO2 to the PaO2, the artery? Why is that?
Yeah, that'd be venous admixture and shunt.
So,
yep. Anatomical shunt and pathological shunt.
And what is the end capillary PO2 roughly? Not the pulmonary capillary, so the end capillary down at the tissue level.
Oh, I think normal value somewhere in the range of kind of 20 or odd, I think, something quite.
So I've got here about,
I've got
here about 40.
Okay.
Good. And then in the mitochondria, I've got here this value of mitochondria is about 4 to 22, depending on where it is. Good. So yeah, again, I've just got the location here, and I just show the stepwise decrease, and what is the reason for each of the stepwise decreases, and these are pretty much, these are a large majority of your causes of hypoxemia can be expressed through this graph. So you can either have low FI, you can have diffusion, you can have shunt or VQ mismatch. And finally, hypoventilation is not described here.
So Lahiri, would you add an extra step onto the graph you've got there for the difference between the addition of saturated vapor pressure?
I think I would actually. Yeah, because as soon as it gets into the lungs, it will change. So you can pretty much do whatever you want, really. And you could put, humidified, I'd put the location as humidified gas in the airway. I haven't done it previously, but I don't see why you wouldn't.
I think the way I'd usually drawn it is like 159 down to 149, which I think the numbers that I just remember.
Yeah, no, I think that's fair, because you're starting from, essentially...
From the atmosphere, yeah. Where I think 21% is 159 point something or other.
Yeah. Okay. So at the end of this, I remember looking up the Pasteur effect, and this guy called Louis Pasteur, who was essentially responsible for the process of anaerobic and oxidative metabolism. So you could decrease or increase the oxygen levels when you're fermenting beer and using yeast, so that if you have more oxygen, you'll produce more yeast. And if you have the oxygen levels lower, then you start producing alcohol. So that's that's where this Pasteur's point came from. So the Pasteur effect is inhibiting the effect of oxygen on the fermentation process. I thought that was just really interesting. And who doesn't like beer? Okay. Let's have a... Yeah, please.
Quick question. Just with going from the alveolar gas where the PO2 is approximately 100 to the M pulmonary capillary blood where the PO2 is almost 100, just slightly below. So we attribute that to a diffusion barrier. In West, it says it's because of some diffusion limitation, which is negligible, but oxygen is perfusion limited. So I just wanted to check it's definitely because of a diffusion barrier. It's not because of a diffusion limitation, which West is suggesting, which doesn't make sense to me.
Can you say the statement in West again?
So West says that the difference between alveolar gas and M pulmonary capillary blood is because of some diffusion limitation, which is negligible. But we all know that oxygen under normal circumstances is perfusion limited, not diffusion limited. Yep. So when we explain this in a viva, should we just say it's because of a diffusion barrier?
So that's a really good question. So what I would do is I would say the facts. Oxygen is perfusion limited normally. So if there is a drop from the alveolus to the end capillary, that drop is a small drop often if there is a diffusion problem, and there's only hypothetical. So in conclusion, that is a drop that can occur in some lungs, but in healthy lungs, generally speaking, there will be a very negligible drop in PaO2. So yeah, it is perfusion limited. In unhealthy lungs, you may get a drop as part of that oxygen cascade diagram.